Alright, in this lesson I want to look at the natural exponential function and also some applications of exponential functions. And remembering what we talked about with exponential functions in general, remember every exponential function has a y-intercept at 1 as long as it hasn't been translated or dilated. But let's take a quick look and remind ourselves of this number e. This is a number that you ran into in Algebra 2. E is approximately 2.71828. It's an irrational number, just like pi is irrational. The definition of e is really this right here as x approaches infinity. Okay? So notice here, this x is going to get larger and larger, this x is going to get larger and larger. If you plug this into your calculator and looked at a table, that value, the bigger x was, would approach this value of 2.718. Okay? Now, another thing, if you remember, that we looked at in our previous lesson, is that another point on any exponential graph is always going to be the point 1 and then whatever the base is. Alright, so if we're looking here at this e to the x base of e, notice it's hitting the point 1e. Okay, now you might ask, what's the point, or why are we using this e, and what's so significant about it? Well, for one thing, it has a special name. It's called the natural exponential function. But the reason why we use e is because of this limiting process as x is approaching infinity. And to kind of explain this a little bit better, I want to look at an example using two formulas that you've seen before. Okay, we have a continuously compounding interest formula. The amount at time t is given by the principal times e to the power, that is the rate as a decimal, the interest rate, times the time. Okay? Now you've run into this formula before, and you probably just memorized it. But we have another formula that's related to it called the compounding interest formula. Notice it's not continuously compounding, but it's going to compound a certain number of times every year. For example, we might compound monthly, in which case, of course, there are 12 months in a year, so n would equal 12. That's actually the most common one if you're looking at banking or things like that. Also, for example, you could have quarterly. That would be every 3 months, so every quarter of the year, so n would be 4. Or semi-annually. Semi means half, so every half of a year, so it's going to compound twice a year. Alright, but you might ask, why, or what's the point? How are these two related? Well, think about what we just saw in our definition of e. We had x in the exponent, and also it was the denominator of the fraction. Okay? Now, I'm not going to get into how the r comes out into the exponent to become this, but you can kind of see the value of e taking shape here in this parenthesis. And what's happening, if you think about continuously compounding, alright, the more often we compound, the bigger n is going to be. So, of course we have semi-annually, quarterly, monthly, we could do daily. What if we did compounding every minute? Alright, then we'd have to figure out how many minutes are in a year, or every second. Well, continuously is even more often than every second. It's every moment. It's continuous. So n would be approaching infinity. Okay? Because no matter how much you break down time, you can always break it down into smaller and smaller increments in order to try to get something that is continuous. Alright? So that's how these are related. Both of these are related not just to finances, but really to anything that is growing, okay? And this is one of the main things I want you to understand here, because this is what's going to allow you to take the knowledge that you have about these formulas and apply it to other formulas, okay? This principle, the P in both cases, this is the starting amount. This is the amount that you're starting with. So if I'm investing $5,000, $5,000 is my starting amount. If I happen to look at the population of a city and I want to see how it's growing over the next 10 years, its population right now would be the starting amount. In fact, sometimes what you see in these formulas, rather than using P, they'll say the amount at time t is the amount at time 0. They'll use that little a sub naught, we call it, or a sub 0, e to the rt. Alright, and we do that sometimes just to take it out of the finances specific application and look at it more generally in terms of anything that can grow. Now, this is for things that are growing at a continuous rate, like the population of a city, for example. If we're just looking at an average rate of growth over a long period of time, we could look at it that way. However, if our rate of growth that we were talking about was, say, an annual rate of growth, we would use this compounding periodically formula. Okay? So, for example, my amount at time t would be the amount at time 0, and then I want you to really understand this parenthesis, okay? Why are we doing the r over n, and why are we doing the t times n power? Because really the basic formula that we have here is 1 plus r to the t power. Alright, and you might say, well, what's with the n's? The n's are really unit conversions. Okay, now I'll use monthly here as an example. Okay, anytime you're given a rate in an investment, it's going to be given as an annual rate. So let's say that we were earning 6% annual interest. Alright, and we were going to invest this thing for, let's say, 5 years. Okay. Now, if we want this to compound monthly, notice these are both in terms of years. So we have a unit issue. A unit of time is not consistent. Alright? Now, you can't really take the compounding number and convert it to an annual because you'll lose some of those compounding events. So what we have to do is convert our annual rate of interest into a monthly rate of interest. Okay? So, of course, if it's 6% per month and there are 12 months, I'm going to do 6% divided by 12, which would be 0.5%, but that's per month. Okay? We're going to earn 0.5% per month. Okay? Likewise, if we're converting our rate to a monthly rate, we need to convert our unit of time into months. Alright, so 5 years times 12 months per year, that means we're going to have 60 months that we are going to be investing this money for. Okay? Now, this formula right here, like I said, it's a generalization of this compounding interest formula, and the key here is you can still think of it this way as long as we have consistent units. Alright, we must have consistent units. So think about how often, and really the key is how often is it going to compound. So let's look at a couple quick examples, and we'll see both determining, alright, is it compounding continuously? Is it compounding over a period of time? Alright, things that compound periodically would be like a population of a city if all you know is the annual percentage rate, okay? Or let's say your company's profits are broken down, and you know that your profits have been growing at a certain percentage each year. Well, there you would set it up using this periodic growth. The continuous is more for things like, say, the growth of a bacteria. This is how they figure out how long a bacteria is going to take before it actually is harmful or is actually going to have the harmful effects. How long can it last in your body? They look at that growth and they can see it, but it's not just growing periodically, it's going to grow just continuously. Same thing with like the growth of a plant or the growth of your hair. If you can figure out the percentage that it's growing, you can then figure out the growth and how long it would be after a certain number of months or something like that. Okay, so let's look at examples here. Here's the first one, just to see both of the methods side by side. We have two options for investing $1,000. So notice we're starting with $1,000. That's going to be our principal, or you could also call it the amount at time 0. The money market account pays 5% compounded monthly. Alright, so in this case, we're going to use this formula right here. Okay, it's compounded monthly, so n equals 12. Of course, your rate is 5%, so that's going to be 0.05. Okay, but then we also have an annuity. An annuity is kind of an interest, or I'm sorry, not an interest, insurance kind of investment. But doesn't matter what it is, it's going to pay 4.8% compounded continuously. So there we're going to use this formula. So we have our rate, which is 0.048. Okay? Now, if you're 18 and you plan on retiring at age 68, which I believe is the current retirement age in the U.S., that means you're going to have this invested for 50 years if you just leave it alone. So T would be 50, and that's going to be the same for both of these. Alright, so let's take a quick look at how we would calculate these. First of all, with the money market account. Alright, we'll call that M&M. Alright, so we set up our formula. The amount at time T is our starting amount times 1 plus, now we need to convert our rate to a monthly rate. So it's 5% per year. So we need to divide it by 12 to convert that into a monthly interest rate. Okay? But then we also need to convert our time into the number of months. So 50 times 12, 50 times 12, 5 times 12 is 60. So this is going to be 600 months over 50 years. Alright, so if you plug this into your calculator, it's going to look something like this. And you'll notice that at the end of 50 years, your little $1,000 investment is now worth a total of $12,119.38. And anytime we're dealing with money, we're going to round to the penny. Alright, so that's how much that money market is going to be worth after 50 years. Okay? Now, the annuity, we'll call that AN. The annuity is continuous interest, so this is the amount at time T. And as you look at it, you'll notice it's a lower interest rate. So the initial thought might be to say, wait, it's 0.2% lower, so of course we'd go with the higher rate. The thing is, though, here we're compounding more often, and the more often you compound, eventually the greater the amount is going to become. Alright, so the question is 50 years enough time for our continuously compounded one to end up larger than the monthly compounded one? And really, is that continuous compounding enough to overcome that 0.2% of a lower rate that we have? Okay, so let's finish plugging this in. It's 1,000 times e to the 0.048 times 50 power. Okay. If we plug this one into our calculators, we have 1,000 times e to the 0.048 times 50 power. And you'll notice in this case we actually only end up with $11,023.18. So $11,023.18. So in this case, actually, that 0.2% was better to take, even though it was compounded less often. Alright, so our best choice is going to be this. Okay? Now let's take another look at an example of one that you've probably worked with in the past, but I want to relate it to our formula here. We have a half-life of 1,599 years for this radioactive radium. We have 25 grams of radium right now. How much will be left in 1,000 years? Okay, well, it's not 1,599 years, or else this would be an easy solution. There would only be 12.5 grams left. But let's look at a formula here. We have that amount at time t is going to equal the amount at time 0 times 1 plus the rate to the t power. Okay, and as long as our rate and our time are in the same units of measure, we don't have to worry about dividing by n or multiplying by n. Alright, and in this case, we have to think about what our rate is. Okay, this is a half-life. And that means that we're only going to have half as much of this radioactive element left after 1,599 years. Okay? Now, that means that we are losing 50% every half-life. And notice here, I'm using this term half-life kind of as a unit of measure. Alright, so my R, I'm going to treat my R as a negative 0.5. Okay? Now, where you have to think about this a little bit is your time. Okay, our time has to be in terms of half-lives. Right now our time is 1,000 years. But we need to do a unit conversion. We are told that one half-life, I'll just put HL for space, one half-life is 1,599 years. Okay? So if I do this, my years cancel out, and I have 1,000 over 1,599 half-lives. Okay, again, now I've converted my rate and my time to be in the same unit of measure. So notice I have 25 grams to start with. I have 1 minus a 0.5, and then that is to the 1,000 divided by 1,599 power. Now, in the past, you may have learned a formula. The amount at time t is your starting amount times 1/2 to the t divided by k power. Notice that's what we did. 1 minus the 50% is the 1/2, and we did the time divided by the k, and k was always your half-life, 1,599, but we didn't really learn why we were doing that. We just learned it as some random formula. The fact of the matter is, it's still based off of the same thing. We just have to do the unit conversion. 50% every half-life, so we convert our time to the number of half-lives. Okay? Now, if we plug this into our calculator, like you see here, we end up with 16.206, or you could say that this is approximately 16.21 grams of radium. Okay, now our answer does make sense because it was less than 1,599 years, so we should still have more than half of it left. Alright, so we should have more than 12 and a half left, so that makes sense, at least from that standpoint. We have 1,621 grams of this radium that's left after 1,000 years. Okay, so now I've given you an example to try for some independent practice. I've given you a model here talking about the value of a Jeep and how its value depreciates or goes down over time. The first thing I want you to do is model this, given that it has a 25% loss of value each year. I kept it a little easy for you in that that's a value per year, and we're talking about T as a number of years here. Okay. I also gave you a table here so you can check your answers. If you get the correct model, then after 1 year it should only be worth $17,978 and so forth. So you can check yourself. Alright, I want you to sketch the graph of this and then also answer some questions here. Some are pretty obvious, but others take some more thought. And I really want you to think through this and try to understand how the exponential growth or decay in this case really impacts the situation. Okay? So let's let you get to that.